In this slide and afterward, we will talk about the error propagation. What we mean is that, let's say we have an error for a variable, and if we have a mathematical operation of this variable with another variable with error, meaning like that we have two numbers with errors, and we have a mathematical operation like multiplication or summation, then this operation will also have a propagated error. So the errors will propagate from these individual two numbers to the mathematical operation result. Let's say we have fx function and assume that x tilde is an approximation of the value x. So there is a discrepancy between these inputs. Also, there is a discrepancy between the function values, and the discrepancy is difference or error. That means delta f x, for instance, and for tilde is equivalent to, in absolute values we can write it, the actual value of the function at x minus the function value for the predicted x. So this predicted x has an error. Here the issue is that we don't know about, we don't know x, which is the true value, and fx, which is the true function value of x. So then we can assume, and we actually assume x tilde, which is the prediction, is close enough to x, because it's just an approximation. And also the prediction of the function value for the prediction is continuous and differentiable. In this case, we can say that we can employ the Taylor series. Then we can employ the Taylor series. Meaning we will have the fx from the predictions. We don't know this one, but we know the prediction value. So this is opposite of the Taylor series we used in the previous slides. We wanted to have the xi plus 1 value by knowing the true value of fxi, but now we know the predicted value fx tilde, so we will use that, and that's why the derivative will be also for the x tilde or the prediction, and the step size is x minus x tilde plus the second term and the others of x tilde again divided by 2 factorial and x minus x tilde square, and it goes to the infinity. So let's truncate after the second term and use only the zeroth and first order terms. Then we can have the difference of fx and fx tilde is equivalent to simply f derivative x tilde and x minus x tilde. Or this is now delta fx tilde equivalent to, here we can consider this in an absolute manner, like absolute fx tilde times delta x tilde. And now we can say that this is the error estimate of, because it's delta discrepancy, it's the error actually of the function, and just estimate of function fx, and this delta is the error estimate of x, the inputs. And on the right hand side you can see a graph that shows the estimated and true error. You can see here that we have a true function, and we actually predicted this with a first order Taylor series because we truncated after the first order. This is a linear approximation. And in here, between the x tilde and x, we have a delta x, which is the error estimate of x. And also there is a difference of the x function value and x tilde function value, this one, and this is actually this delta x. And we say that we can calculate this by the derivative, this one, times delta x. So this is that simple actually, and the slope of this will give us basically f delta x divided by delta x, which is the derivative, and derivative is a tangent to the function. So that's why it works well for this error propagation actually. Example 4.5 is an example for error propagation with a single variable. Let's show this. And here you can see that the estimates of the x value is 2.5 and delta x, the error is 0.01, meaning that x is basically summation of this with this one, the true value. And the function is x to the power 3. So we can calculate the 2.5 value function value of it actually by simply writing it down. If we write it down here, we can get the estimation of 2.5 from the true function, as you can see here. 2.5 cube is equivalent to 15.625. So let's keep this in mind, and we will use the formulation that we derived in the previous slide, which is delta fx tilde is equivalent to f derivative x tilde and delta x. Here we note some values. This delta x is 0.01 given in question over here, and this fx derivative can be determined from the derivative of this. Let's find the derivative. F prime x is equivalent to 3x2, and for x 2.5 x tilde, f prime 2.5 is equivalent to 3 times 2.5, 3 times 2.5 square. So we can simply write this down here, and eventually we can calculate delta fx, which is, by the multiplication of these, it's 0.1875. We calculated this. Now we can get the fx value result using the first order Taylor series. So n equals 1 Taylor series. This series says the fx is equivalent to fx tilde plus f prime x tilde delta x tilde. And we know that this value is this. The entire multiplication of this is 0.1875. and this is 2.5. Then the fx value is, here we calculated that already, 15,625. In this case, we can simply find fx as 15.625 plus minus 0.1875. So we add here plus and minus to show that this is the error and the fx value is either minimum or maximum of this by summing or subtracting this from this value. So which means equals between, if we subtract the result, it's 15.4375, and if we sum the error, 15.8125. Okay, so we can show that if our x value is x tilde minus delta x, meaning 2.5 minus 0.01 equals 2.49, then our f function result here, 2.49 is equivalent to 15.4382. And if x is equivalent to x tilde plus delta x tilde, because it can be plus or minus, 2.5 plus 0.01, which becomes 2.51. Then if we use the function, the result is 2.51, 15.8132. And if we used just this formulation with the Taylor series, we can compare the predictions. These are the predictions. And these are the exact errors, we can say. You can see that, let's compare this with this one because these are the minimums. You can see they are very similar. These are also very similar. So the comparison shows that n equals 1 or first order Taylor series gives fairly close estimates.